Screws are used for fastening and for transmitting power. Or motion. In each case, the friction developed in the threads largely determines the action of the forces. The friction developed in the threads largely determines the action of the screw. For transmitting power or for motion, the square thread is more efficient. The square thread is more efficient than the V thread. And the analysis here is confined to the square thread, the force analysis. Consider the square thread jack, this figure. Consider the square threaded jack shown in this picture under the action of the axial load W and a moment M applied about the axis of the screw as shown in the picture. The screw has a load L, advancement per revolution, has a lead L as shown here, L, lead L, advancement per revolution. And a mean radius R. Mean radius R. The force are exerted by the thread of the jack frame on a small representative portion of the screw threaded is shown in the free body diagram here. Similar reaction exists on all segments of the screw thread where contact occurs with the thread of the base. If M is just sufficient to turn the screw, the thread of the screw will slide around and up on the fixed thread of the frame. The angle phi made by R with the normal to the thread is the angle of friction. This phi tangent angle of friction normal to a screw thread. So that phi equals to tangent inverse mu, or for the small angles phi equals to mu in the radians. The moment of R about the vertical axis of a screw is can be calculated from the next free body diagram. To raise load, the moment of R about the vertical axis with this component M R about the vertical equals to R multiplies to the sinus alpha plus phi. Alpha is the tangent inverse L on 2PR. And the total moments due to the R reaction on the thread is sigma R sinus phi. Since R appears in each term, we may factor it out. The moment equilibrium equation for the screw can be obtained as result. M sigma R. Equilibrium forces in the axial direction further require also this equation that W equals to R for the equilibrium condition, which is so we're making a fraction relation between these two relation. R tangent alpha plus phi, or M equals to WR tangent. To determine the helix angle alpha, tangent inverse leads on 2PR, which are the geometric specification of the screw. We may use the warped thread of the screw as an alternative model to simulate the action of the entire screw, as shown in the picture here. For the condition for consider this picture, the rise load, we may use the unwrapped thread of the screw as an alternative model to simulate the action of the entire screw. The equivalent force required to push the movable thread up the fixed incline is P the equivalence, let me provide the next picture. The equivalent force required to push the movable thread up the fixed incline is and the triangular force vector gives the equations M equals to WR tangent phi plus alpha. Condition for unwinding in the next section.